So how do we find cubic equations? Well, you can be given a graph or you could be given points, and either way you're going to do the same thing. If you think about quadratics and you think about how you find the graph of those, so sometimes with the quadratic you might be given the turning point and another point. So you'd write the equation in turning point form with the dilation factor at the front, and then put the information you know about the turning point into the equation, and then substitute in the other point to find out the dilation factor. Alternatively, you may be given two x-intercepts and another point. If that's the case, then you're going to write it in factorized form with a out the front, dilation factor, and then you're going to substitute in the other point to find out what the dilation of that is. It's pretty much the same with cubics. So with cubics, this one here, as we can see, we've got three intercept points. One intercept point, and we've got one that touches, so you could say almost two, and another point. We also have the y-intercept, which is good. So you've really got almost 2 points, but this one's actually given us coordinates, so I'd use that one. So we should be looking at these and thinking about how we're best going to solve. So really what we do know is obviously I'm going to write this out in factorized form. Now I know I've got a and I know I've got 1 point. Now this crosses the axis. So that's going to be, don't forget the null factor law, because it's -1, it's going to be x plus 1, because if I substitute in -1, that's going to make it 0, which will then be 0 times anything will get me to that point. Over here we also have a turning point on the x equals 2. So I know it's going to be x minus 2. And that's going to be squared, because remember if it's a turning point, it is squared. Again, if I substitute in 2 positive, 2 minus 2 is 0, 0 squared is 0, 0 times anything equals 0, so it's still going to give me that. So I've got this now. This will be my first step that I've got to recognize that I've got these. Now this could have been telling me that the graph cuts at x-intercept of -1 and touches the x-axis at x equals 2, and I can still do this. So this could have been a word equation, or it could be the graph here and trying to figure it out. Next step is to find the dilation factor. So what I need to do now is really just sub in the 0.32 to find the dilation factor. So I'm literally just going to substitute in y equals 2. Whoops, that should be equals. What do we got? A. Then we've got x is 3, so it's 3 plus 1 and 3 minus 2 all squared. Don't forget BIDMAS, that's going to be 4, that's going to be 1. 1 squared is 3 minus 1, isn't it? It looks like a 1 there. 3 minus 2 is 1, yep. Okay, and that's going to be a, and that's all positive, yep. So equals 2, that's going to be 4a. Therefore, a will equal a half. So moving on to this next question. Here, we're going to assume that this is a point of inflection here. I mean, if you look at this gradient kind of hits 0. And if we read the coordinates off here, it's -1, 2. So here, this is kind of like with the quadratics, I can think of it as almost like turning point form, but we call this stationary point of inflection. And that is always written in the form of, with your dilation, x is going to be plus or minus where your x translation, we've translated this in the x direction, so it's gone to -1, so it's going to be plus 1, which is exactly the same thing as the quadratic, and we've translated 2 units up, and that needs to be cubed. Now I've got my graph. Now I can just substitute in another point, and I can't really tell what point that goes through, but they've given me a point down here. So -2 equals a bracket 1 plus 1 all cubed plus 2. That's going to give me 2. So 2 cubed is 8. So that's going to equal 8a plus 2. Now you can move the 2 earlier if you want. They did that in the worked example. Doesn't really matter. Now I'm going to minus 2 on both sides. Minus 4 equals 8a. And we're going to find that now a equals -a half. And that's how you can find that. So again, now I've written this as y equals -a half x plus 1 all cubed plus 2. Now if I had to write this in the form of, let's just say y equals ax cubed plus bx squared plus cx plus d, I would have to expand this, okay? Once I expand this, then I could write it in this form. However, I didn't say that, so I'm happy with that one there. So with example 32, this would be quite long to do by hand, but you could do it by hand if you had to. I mean, if you had to, you would have to make 4 different equations where you would literally say, this, you put in f1, that equals 0. So obviously it's going to be, 0 equals A plus B plus C plus D. We put in 2 equals -7, so -7 equals, what's 2 cubed is 8, so it'll be 8A. 2 squared would be 4 plus 4B plus 2C plus D, okay? And you'd keep on going on. So you put 4 in there, 4 cubed, would be 4 cubed A plus 4 squared B plus 4C plus D. And then you could do simultaneous equations, which would be really long. Wouldn't suggest doing it. But on your CAS, one thing you can do is actually define what the equation is, follow this one through. You can put in your values and it will do it for you. Alternatively, you could also on your CAS, I suppose, create all these equations. It would be a bit longer, hence this way's a bit quicker on the CAS, but you could do all those, and solve for A, B, C, and D variables. However, that would be quite long because you'd need to figure out all these equations and put those in, where this step here is a lot quicker. So just follow that one and go through there. Don't forget then with cubics, when you're actually given either information, there's information about touching the axis, so that should be a squared point. If it cuts the axis, it's just a one linear point. If it talks about a stationary point of inflection, that is where it's basically it inflexes and the gradient gets to 0. So we'll put it in that turning point form of a quadratic. We don't really call it turning point form, but we'll just put in the perfect cube form, and obviously it translates the same way. So I'll pull on that prior knowledge that you know from that, because it really is easily to transfer across, and hopefully it won't be too difficult. Don't always forget, you always need to find your dilation factor. So you're always going to need another point to substitute in. That is, if it's in that stationary point of inflection, you're going to write it in that term, and you're not going to use that stationary point to substitute in to find your dilation factor. Similarly, if it cuts through the axis 3 times, or it touches once and cuts once, you're going to write linear factors. You can write 3 of those, or 2 of those where one of them squared, which is really 3 linear factors. And then you'll need to find another point somewhere to find the dilation factor. Now that could be your y-intercept. You could substitute in your y-intercept as well to also find that. So that's pretty much that on this. Good luck, and cubics are another world of maths that make it great and interesting. I love them.